So for today's lecture, I'm delighted to introduce Andrew Senior from DeepMind. Andrew's going to do both lectures this week. Today's going to talk about automated speech recognition, so ASR, and on Thursday I think it will be TTS, so text-to-speech, the two sides of the sort of speech processing coin. So Andrew, I think, did his PhD in Cambridge many years ago, then has been working in industry at IBM and then for a long time at Google. Andrew's the perfect person to have doing this lecture because he actually was quite instrumental in building out Google's deep learning speech pipeline, which I think was one of the first deep learning speech systems to be deployed. So thank you, Andrew. Take it away.
Thank you. Thanks, Phil. Thank you very much for inviting me here. So yes, I'm going to cover speech recognition today and possibly overlapping a little bit onto Thursday, and then on Thursday I'll talk more about text-to-speech. And as Phil said, I worked in speech recognition. I was in Google's speech group for 7 years, working in New York. The speech group is sort of split between New York and Mountain View for speech recognition, and then speech synthesis is done in London. So I work mostly on speech recognition and a little bit on speech synthesis. So I'm going to talk a little bit about speech. What is speech? What kind of representations do we use? A very brief history of the sort of progression of different methods that have been used for speech recognition. And then talk in more detail about probabilistic speech recognition, and then get into the detail, some sort of the baseline system, which is Gaussian mixture models, and then really get into some more details with neural networks. Although I'm sort of assuming that you've got the basics of neural networks, so in a lot of cases it's just a case of taking a standard neural network and applying it to speech. And then I'll talk about some of the particular peculiarities of doing speech with neural networks as opposed to other kinds of neural network tasks. So particular losses that we get because we're working with a sequence rather than, say, it's particular exemplar classification, and then you'll see some of the techniques overlap a lot with the other NLP techniques that have been covered elsewhere in the course. So basically there are two problems I'm going to talk about. The first is speech recognition, which takes the waveform, an acoustic waveform, and we're trying to turn that into some kind of text. And even the definition of what we mean by text is a little bit vague. You have to specify that. Like punctuation, we don't pronounce the punctuation. But when you see a written form, you expect to see capitalizations, commas, periods, and so on. So that's a sort of a separate task, is just recognizing the words that I say would give you a written form. But to make it nicely formatted text that you might want to display, say dictation and so on, there's an extra NLP task there on top of just doing the recognition. The converse problem, text-to-speech or speech synthesis, goes from the text and goes to the waveform, tries to make an intelligible signal that people can understand. As I say, we'll cover that more on Thursday. So there's a whole range of related problems. So within automatic speech recognition, there are lots of sort of subcategories or specializations that make the different parts of the problem more difficult. So there's a difference between the style of speech. So a lot of early speech recognition was done with read speech versus spontaneous speech. It's a lot easier to recognize something that's been read from a script. The original databases were captured by giving people text and asking them to read it in studio conditions, which made those databases easier to recognize. Vocabulary has increased over time. So it used to be that large vocabulary was 1,000 words. Then it became 65,000 words. And now I think the Google speech recognition system has a nominal vocabulary of 4.5 million words. Now, there aren't really that many words, but we end up with that many text tokens just because we train our language models on very large corpora of text, and there are lots of typos and URLs and all kinds of things in that text. So we end up with this vast number of text tokens, and we just treat them as though they're all legitimate words because we don't have a good system for rejecting the junk, and people might say any of those things that we found on the web. Speech and noise is becoming more and more of a relevant topic. As speech recognition has got better and better in the last 10 years, then noise has become one of the salient problems of if I want to speak to my phone, then if there's background, a fan, then that makes it hard. But if there's somebody speaking in the background, then that makes it even harder because the signals are very similar. And then you have to distinguish between the two sets of speech, which is the one that I actually want to pay attention to. So there are different kinds of noise. Periodic noise, babble noise is often used to sort of simulate speech. And then far field has also become more relevant as we got better at doing speech recognition in general. We focused initially on speech recognition with a close-talk microphone, like a headset, or when you hold the phone to your, close to your lips. That became very good. Now we want things like the Amazon Echo, the Google Home device, where we want to be able to speak to it across the room. And that's becoming achievable, this sort of far field recognition in noise. There's also low-resource speech recognition. If you want to recognize a language that nobody's built a speech recognition system before, how little data do you need to collect? There are vast resources we'll come to for training a speech recognition system in English. But if you want to field a system for Zulu, which we did, then there's very little data there to actually train a system. How little can you get away with in terms of both the actual recorded speech, the transcriptions of where somebody has written what is said in those speech utterances, but also things like pronunciation dictionaries to know how to take a word from the written form to the spoken form. And things like building language models and vocabulary lists. We also want to be accent independent, so recognizing English regardless of what kind of accent somebody is speaking. On a phone we may have a label of which language they want to speak, but we won't know what accent they're going to speak to. We're going to sell our phones to people from London and Scotland and America and New Zealand and so on. They're all going to have different accents. We want to have a single model, ideally, that can cope with all of those. And we want to be speaker adaptive, ideally, that the initial speech recognition systems were speaker dependent. They were trained on a particular speaker. You'd spend several hours reading out documents to your IBM Via Voice dictation system. Now we have systems that work pretty well for anybody, but can we get some extra performance by training on a specific speaker? As we listen to them over time, can we get better at recognizing how they say particular things? For text-to-speech, there are also a variety of problems. We've got low resource again. How little resources can you get away with to build a text-to-speech system? And prosody is still a big problem. That how do you know what prosody to pronounce something with? Like just the intonation of a sentence can change whether it's a statement or a question. How can you get the markup and then use that markup to actually change the way something is said so that it's said realistically and make it sound conversational? So, for instance, the Google speech synthesis voice, they went and redid all the recordings when they went from just doing things like driving directions and when they started to release a conversational agent that was supposed to be a bit more spontaneous and engaging. Then they just had recorded the wrong kind of data, so they went and recorded a whole new data set. And then there are many other related tasks that we're not really going to get into in these lectures, but use a lot of the similar techniques and maybe used in parallel with these other things. So speaker identification, knowing who is speaking. So if I say, OK, Google to my phone, then I want it only to respond to my voice so that nobody gets into my private information. And I also don't want my voice to set off everybody else's phones when I say OK, Google in public, for instance. Then speech enhancement is just taking speech and noise and turning it into cleaner speech, which you may want to do even for telephone channel, making something more intelligible, but can also be the front end to a speech recognition system. And then speech separation is trying to extract one person's speech when there are multiple sources of sound, particularly when there are multiple speakers speaking at once. So the so-called cocktail party effect, where you want to attend to one person's speech and ignore everybody else whose speech may be equally loud. And as people, we're very good at doing that. And machine systems are not very good at that yet so far. So now I'm going to talk about the kind of representations that we use for the acoustic signal. So speech, it's waves of changing air pressure. You've got the sound waves traveling through the air. It's realized through excitation from the vocal cords when you've got a voiced sound, a vowel. So coming from in the throat, and you modulate that sound by changing the vocal tract. So you're moving both the shape of the mouth and the articulators, the tongue, the teeth, and the lips to change the resonant qualities of the vocal tract, to change the sound. And you also get consonants by closing the mouth, or fricatives when you close the teeth to the lips and so on. And you can parameterize this as a whole field of study of linguistics. I'm not a linguistic expert, and there's this famous quote from the IBM speech recognition that every time you fire a linguist, your recognition rate improves. But basically, as they started concentrating on data rather than handcrafted rules, then they could improve the quality of the speech recognition. But there's still a lot of linguistic knowledge in a typical state-of-the-art system these days. Although increasingly we're still trying to get rid of that linguistic hand-coded knowledge. So you have this wave of sound pressure in space. It's converted to voltage with a microphone, and then we sample that with an analog to digital converter, and we get these samples, usually regularly spaced in time, and we're sampling a voltage as the amplitude of the wave. So we end up with this quantized signal, and basically everything I'm going to be talking about is digital signals. The speech occurs in a limited range of frequencies, so human hearing is roughly 50 hertz to 20 kilohertz, and human speech, the sort of fundamental frequencies go from, I think, 85 hertz to about 300 hertz, and then there are harmonics that go up to higher frequencies. Typically, telephone bandwidth is good enough, pretty good for speech, although it does cut out some of the higher frequencies and the lower frequencies, but it's still intelligible for the most part. That has an 8 kilohertz sampling rate, and roughly speaking, the bandwidth is 300 hertz to 4 kilohertz. You can also change the resolution that you sample at. You can actually understand 1 bit per sample speech, but typically we sample it much higher. A CD is 44 kilohertz, 16 bits per sample, and most speech signals that we're going to process are 16 kilohertz or higher, increasingly 20 kilohertz, and 16 bits per sample. That's a lot of data to handle. And particularly with traditional systems like Gaussian mixture models and so on, we need that to be a very low-dimensional signal to be able to do statistical modeling of the signal. That's less so with neural networks, but we still want to have a compact representation to make it easy to train models and so on. So the first thing that people turn to is Fourier analysis. So you do a fast Fourier transform on that signal. Typically, you take a window of the signal and do a discrete Fourier transform of the samples within that window. Say 400 samples, which would be a 25 millisecond window. You do a fast Fourier transform and work out the frequency components of that signal. So this is a visualization of a fast Fourier transform of a speech signal. So the brighter colors are higher energy in the frequency. So the frequency here goes from 0 to 10 kilohertz, and time is across the x-axis. And you get these bright bands, which are the formant frequencies. So when you're saying a vowel, you get these strong signals at a particular frequency. So a higher pitched voice will have a higher frequency. It will be higher up on this graph. And then you get the resonances at regular intervals above that fundamental frequency. And there are people who can actually read speech from these spectrograms. There was a very famous course at MIT, which sort of lots of speech PhD students at MIT used to take, where they would teach you to actually read spectrograms. So you'd actually be able to look at this and be able to work out what the individual sounds were. And that shows that this is a representation that is sufficient for some kind of speech recognition. And you see, we've now turned an audio problem into an image problem, so you can start thinking of applying image recognition techniques to this signal. Although obviously the x-axis is time, it can go on arbitrarily long. So we're processing time signals, but we can think of them as images. We've got a two-dimensional image with an intensity. And the frequency and the time ranges are discretized. But the FFT is still too high dimensional. So we may have, say, 512 frequency values. We take these 25 millisecond windows, but we typically overlap them. We generate them every 10 milliseconds. So we're generating, say, these 512 points every 10 milliseconds, 100 times a second. We want a way to dimensionality reduce that. And there was this observation that human hearing isn't linear. It's logarithmic, particularly for higher frequencies. It's considered to be more linear human perception for lower frequencies. So there was this MEL scale that was devised as a way of warping the linear frequency domain into a more natural perceptive based basis. And this is the formula that's in the MEL scale. MEL is not a proper name. It's often capitalized, but it's just MEL as in melody, as a frequency domain signal. And then we take logs. So basically, we take local averages with these windows. So these triangular windowing functions are weighted averages of these different frequency bands. So in the lower frequency bands, we have these very narrow filters, and they're all regularly spaced. And then as we go to higher frequencies, then they get much broader. They're logarithmic. And we take these weighted averages. So we can reduce the dimensionality of our 512-point FFT down to, say, 40 dimensions might be typical. And those would be log MEL features. And those are the main features that are used for speech recognition systems, neural network speech recognition systems. But for a traditional system, again, it's still too high dimensional. You've got these 40-dimensional features every 10 milliseconds. So people took the discrete cosine transform of these MEL filter banks, and that gives a more whitened and low-dimensional representation. So typically people would take the first 13 MEL frequency Capstral coefficient. Basically, Capstral is when you take the discrete cosine of a spectrum. And it's similar to taking the principal components. So typically, a Gaussian mixture model system would use 13 of these coefficients. There's another representation called perceptual linear prediction, which is similar performance. And it may be common to actually stack many of these frames together. So we took them every 10 milliseconds. We may take a range of, say, 2 frames, 10 frames. Particularly for Gaussian mixture models, to model the dynamics of the signal, people took what are called deltas, where you take a local difference. So the frame at time t minus the frame at time t minus 1. And then by doing differences of differences, you actually get a sort of a curvature, and you concatenate these 3 representations, the MFCCs, the deltas, and the delta-deltas, to get you, in this case, a 39-dimensional representation of the signal. And in more sophisticated systems, you might actually learn a linear projection with linear discriminant analysis. So that's like PCA, but where you use the class labels that you have for a speech signal. If you have the labels, you can use LDA to learn a representative basis onto which you can project these features. So you might stack 9 of these vectors together, which is 117 dimensions, learn a linear projection, and end up again with 39 dimensions, which is manageable with the Gaussian mixture model system. Now with neural networks, we can handle much higher dimensional features. So we may just stack 26 of these features. Our fully connected neural network system took 26 features. So that's 275 milliseconds of speech represented at once, and did a classification based on that for 1 frame of that speech. And we repeat that classification every 10 milliseconds. Now we'll come to convolutional networks and LSTMs. We have slightly different frame stacking. So we have 8 is typical for our current production system with an LSTM. So this is just an outline of sort of speech recognition technology. So there was the system dynamic time warping, which is basically stretching templates to match a speech signal. So you take record a speech signal, you turn it into some frequency representation, and have a distance measure and compare it to a template, where you know the time is going to vary because people say things at different rates. So you allowed dynamic time warping with the Viterbi algorithm, and you just find a best fit. That was back in the 1960s. In the 1970s, hidden Markov models were developed, and the Dragon system was written to do speech recognition with hidden Markov models. We got multi-layer perceptrons in the 80s, and people immediately started applying that to speech recognition. But Gaussian mixture models with HMMs took over as the dominant paradigm for about 15 years. They just outperformed the neural networks, and we didn't have good training systems for the neural networks. It's much easier to train a Gaussian mixture model system. So people basically forgot about neural networks for speech recognition pretty much. In the early 2000s, people started applying them to generate features. So learning features instead of these hand-coded MFCCs and so on. Can you learn features, but you would still feed them into a Gaussian mixture model. And then with deep networks, people again tried speech recognition. There were initial good results with Timid, which is a tiny database that's sort of not really considered by speech recognition researchers because it's so small. People are working on much bigger systems. But then people took these DNN systems, applied them to larger systems, and started getting good results on large vocabulary speech recognition. We weren't the first to do that at Google, but we were the first to take these and actually put it into production. And then we iterated on that, and every year there would be pretty dramatic improvements in speech recognition quality. And everybody started doing deep neural networks. And then now, increasingly, it's recurrent neural networks, although there's still quite a lot of convolutional networks being used for speech recognition. My supervisor was working on speech recognition using recurrent neural networks in the 1990s, and I applied it to handwriting recognition. And then there was this resurgence of interest in recurrent neural networks. And now there are new models based on recurrent neural networks, but things like attention, listen, attend, and spell, which uses attention, and the neural transducer, which is a variant on these attention-based models. So speech, it's evolved as a method of communication. It's there to convey information. We can organize it in various ways. So we can look at sentences, so the sort of the fundamental unit that we try to recognize in speech recognition. The sentences, we can divide them into words. And of course, this is language dependent. The sort of definition of a word may vary depending on what language you're talking about. The minimal unit is considered to be a phoneme. That's basically the unit that if you change it, it can change the meaning of a word. So you can have two words that are different in meaning, and they only differ by this minimal unit, then that defines a phoneme. So cat and bat, you can tell that the k and b are phonemes because they distinguish these two words. So for English, we may have, say, 40 to 60 of these sounds. The actual set of sounds that you have varies depending on the language. There are some attempts at universal representation. So there's the International Phonetic Alphabet, which uses all kinds of special symbols to represent these phonemes across all languages. And then there's an ASCII version of that called XSAMPA, which we typically use in a computer-based system. One problem that we have to deal with is homophones, which are these distinct words which have the same pronunciation. So we want to be able to disambiguate these. Basically, we can only do this by context. There versus there, these two spellings, or three spellings of there. And then there's also this sort of meta-linguistic information, the prosody, how you say something. It's not the actual words you say, but it can convey meaning. For instance, I can turn something into a question just by changing the intonation, but saying exactly the same words. There's a lot of work studying prosody, but almost no work actually applying it within speech recognition. So actually distinguishing somebody saying a question from not a question when they say exactly the same words, there's very little use of that. Basically, we're just recognizing the words, and then we produce pure text and feed it into some natural language processing system. That's very, very hard to get useful information out of the prosody still. This slide is just to explain datasets, the kind of datasets that we're using for speech. It started out with Timit, was a very widely used dataset. It's still commonly used for machine learning systems, just as a sort of proof of concept system for working on audio. There, the phone boundaries have been hand marked. So you get your acoustic waveform, and people have actually marked where they think the boundary between the k and the a sound is, which is rather ambiguous, but it did help bootstrap a lot of research, having that timing information enable people to train systems to distinguish different phonemes. Then people collected more and more data, so there's the Wall Street Journal, which is people reading Wall Street Journal, and in fact, when I was at Cambridge, I participated in an English version, a British English version of that, where we recorded British accents, but we used the same text. Then broadcast news, a little bit bigger, and then switchboard got a lot bigger, and that's telephone speech and spontaneous speech rather than read speech. So all of these things, they're getting bigger vocabulary, they're getting more difficult. Spontaneous speech instead of read speech, more speakers to vary the conditions to get closer and closer to sort of a general speech recognition system. With the Google Voice Search system, which is now part of Google Now and the Google Voice Assistant, we typically use 2,000 hours of speech, which was 3 million utterances of real traffic. So we took real people's utterances, we had them transcribed. There's no identifying information attached to that information. We use the hand-transcribed labels to label the speech, and that's constantly refreshed. So basically, an utterance that's recorded by Google, if you've opted in to have it recorded, preserved to help speech recognition, which I think is the default, then it gets saved, but it only gets saved for up to 2 years. So every 6 months or so, then we lose some of our data, and we have to generate a new training set. There's a system from Baidu that collected 5,000 hours of read speech and also combined that with the switchboard dataset. They also wanted to deal with the additive noise problem, the fact that they wanted to use their system in noise. So they actually had people speaking with headphones on. The headphones would play loud noise so that the people's speech would be affected by that noise. So we changed the way we speak when we speak in noise. So they actually wanted to capture that effect, how the voice gets changed in noise, by recording the speech with the people hearing noise, but the noise wasn't actually present in the speech because the people were speaking to a microphone, that they could only hear the noise on the headsets. And then they could add in a controlled amount of noise later on top of that to simulate the effect of noise for the machine learning system. And that's the kind of thing that we do also in Google Voice Search. And then one of the most recent papers from Google is on YouTube speech recognition. And there they've captured a data set of 125,000 hours of labeled speech, basically because people upload captions to YouTube videos. We can use the speech recognition system to get the timing right for those videos. And when the text does match the speech, then we can use it as a training for a new speech recognition system. So now I'm going to talk a little bit more about how we model speech as a probability problem. So we have a speech signal that we've represented by some kind of observation sequence. So that might be our MFCCs, our log-mel vectors. So we're guessing the sequence of vectors over time. And for a given utterance, suppose we have it bounded, we want to find the most likely word sequence, which I'm going to call W hat. And we're going to model the speech production system with a hidden Markov model. So a Markov model is typically represented by a set of states. So this is an image across the bottom. Here, I've got a start of sentence marker S. And then I've got phonetic units here. So I've represented this by a graph of phonetic units. It says the cat, in this case, where each unit is a phone. So we have, with a hidden Markov model, we have a set of discrete states. The system is in one of these states and transitions from one state to another over time. And the thing about a hidden Markov model is the the state sequence is hidden. We don't actually know at a given time what state the model is in. All we get to see is the observations that come out. So as it transitions from state to state, we get acoustic events that come out, which are our observation vectors. So we may spend some time in the state. So we emit a few frames of v sounds. Then we'll transition to the state, emit some sounds, and then k, and so on. So all we see is the observations, and we want to infer the underlying state sequence as a way of getting to the underlying word sequence. And the assumption is it's a Markovian process, so basically the transition probability is only determined by the current state. And in modern speech systems, we don't really worry too much about the transition probabilities of going from one state to another or staying in the same state. But we do care about transition probabilities when there's a branch. So in general speech, I can say a sequence of words. I can say the, and then the next word could be cat or it could be dog. There's a branching there in the real graph that is of the graph of all potential utterances. We want to recover the path through that graph. And those transition probabilities then are important. Those become the language model probabilities that you've learned about in language modeling. So we want to choose, actually, let me come back to what the phonetic units were. The image that I just showed had phones, the phonemes, as the fundamental units. So we went from k to a to t. So that's my top line here. But people found that you might want to split the phonemes into multiple states. So the beginning of a k, the acoustic realizations are going to be different to the frames that you emit in the middle of a k sound. So we may split the k sound into 3 states. That's typical for a modern speech recognition system. There's been a lot of work on trying to learn how many states you should have, but typically people just use 3 states. Modeling the onset and the middle and the end separately. But we can also make that context dependent, where people recognize that how I say a k is going to be different if it's in the word cat and if it's in cone, say. Even though the phone is nominally the same, it's a k sound, the actual realization will be different, and the actual distribution that you observe, if you actually plotted the vectors, you would see a slightly different distribution. Since we want to model these distributions probabilistically, people came up with the idea of context-dependent states, which I'll give some more detail of in the next slide. So there you've split the k into 3, beginning, middle, and end, and then each of those you model according to the context. Or you can just have one whole phone model, but model that according to the context, which is a context-dependent phone. People also use diphones, where you model a transition, so from k to a in cat. You model from the middle of the k to the middle of the a. And that's particularly used in text-to-speech, but people have used it for speech recognition. People have also looked at modeling whole syllables. If you have enough data, you can build a model per syllable instead of per phone. The beauty of the phone is that there are a very limited number, say 40 or to 50 in English. When you start looking at the number of syllables, then you get a much larger number, and it's much harder to model them. There's also work being looked at using word parts, and there's work on using word parts for machine translation, but that's also been applied to speech recognition. And then what a lot of people would prefer to do is just use written characters, which we call graphemes. So if you can work in the written domain, where you're just modeling characters, then you don't have to explicitly have a lexicon which maps from the written characters to the pronunciation, which is typical for an English speech recognition system. So you have to build up all this knowledge of, if I see the word Polish, then it can be pronounced Polish, but it could also be pronounced Polish. So basically, we have a pronunciation dictionary as part of a speech recognition system. If you could just directly model from characters and have the system learn all that pronunciation as a side effect of training, that would be great. It would be much easier to build these low-resource systems when you come to a new language. Some languages are entirely phonetic. So Turkish and Italian, you can model very easily from characters because the pronunciation is very consistent. If you see a sequence of characters, you can pretty much tell how it's going to be pronounced. But we all know in English there are things like OUGH that you have to know which word you're talking about as to know how it's pronounced. So we found consistently you get about a 10% advantage by modeling if you model the phones, given that we have these great pronunciation dictionaries that we've built over time. But other groups, particularly people who take the machine learning approach, want to start a speech system with very little resources, then you can get a long way by modeling the characters directly. And also, recently people have looked at modeling whole words, where you just train a model for each word individually. And again, this YouTube paper that I just mentioned, where they had 125,000 hours of speech, they could build a model for every single word in I think a 500,000 word vocabulary, just because they had so much data. And there were still words that they weren't modeling that we would know how to model if we had a phonetic system. But there were so few of those that the errors caused by not knowing a word became negligible compared to the advantage in modeling that they got by modeling each word individually. So the choice of the phonetic units that you use is going to depend on the language, the size of the data set, the task that you care about, and the resources that you have available. But most speech recognition systems use a phonetic approach, and pretty much they use context-dependent states. I did some work with LSTMs using context-dependent phones, where I found that they were at least as good as context-dependent states. But most systems these days would use context-dependent states still, even though those are hangover from the Gaussian mixture model days. Context-dependent phone clustering, this is how you model a K according to its the neighboring phones. The realization will change. So we can model every single potential phone in every potential context. Say if we have 42 phones, then each of the 3 states for that K sound can have 42 squared realizations, depending on what the previous phone was and the following phone. So altogether, we end up with this 3 times 42 cubed possible triphones, as they're called, phone within a preceding and a following context. Most of those we won't ever see, and some of those we will see in testing and not find in training. So you have to come up with a system to cluster those together so that you can model similar things together as to have the maximal discrimination between these different categories. So people typically build a decision tree to cluster together these 3 times 42 cubed potential units and put similar things together according to a tree clustering algorithm. So with these tree clustering algorithms, we can go from our 42 phones to pretty much an arbitrary number of phonetic units that we're going to use. So systems typically use around 10,000 of these phonetic units. And by choosing how aggressively to cluster, you can choose how many of these units to use. So a system that runs on a server with lots of memory may use a lot more than, say, the system that runs on your phone and needs to run fast and in a small amount of memory. You can choose the number of phonetic units that you use. So this is sometimes called the fundamental equation of speech recognition. Basically, we want to find the most likely word sequence out of all possible word sequences that are realizable in the language, given we have an observation sequence of acoustic vectors. And this we do by taking the maximum likelihood word sequence given the observations, and we can decompose this into the argmax of that is going to be the argmax of this product, where we take the probability of the observation sequence given the word and the probability of the word sequence. So we've got an acoustic model score where we're modeling the acoustics assuming we know the word sequence, and a language model score that models the likelihood of a sequence of words. In the acoustic model score, we can break down into possible sequences across the phonetic units that we're using. So in this case, we've got the probability of observation given a context-dependent state, and the probability of the context-dependent state given the phone, and the probability of the phone sequence given the word. So we have a phone sequence, and that can be dependent, we can have multiple pronunciations that give, for a given word realization, we can have a branch of, there are two different ways that this might be pronounced, like two different accents, Polish versus Polish, say. So we're building this probabilistic system. And we can model the word sequences with a language model. So typically, the product of a word sequence is decomposed into the unigram probability of the first word, and then the probability of each successive word given the preceding words. So this is called the chain rule. And we can choose, with, say, an n-gram language model, we choose how many context words we take into account. So we don't necessarily go all the way from W0 to WI minus 1 as the context. We may only take, say, WI minus 1, condition on that for WI, and that would be the bigram probability. And then with longer and longer context, we can get better and better modeling, but you have to have all the smoothing and back off to be able to handle the things that you don't observe in your training data. And then we could also do LSTM language modeling, neural network language models. I'm not going to go into any of those things, but all of those techniques that you've learned for language modeling can be applied in speech recognition. Typically, you want speech recognition to run very fast, so it's actually quite difficult to use an LSTM language model in search. N-grams are very fast because they're just a lookup. So typically, we use an n-gram in search, and then we may re-rank the hypotheses using a more detailed language model that gives better performance, like an LSTM. And typically, the best results are being got from a combination of an n-gram language model and an LSTM language model, or some other kind of discriminative language model. So one way of looking at speech recognition is as transduction. So we're basically mapping one signal into another, and we've got this hierarchy of representations. So at the basic level, we've got the audio. We can map that into features. We can map those features into these acoustic states. The states can be mapped into phonemes, the phonemes into words. Ultimately, what we care about for speech recognition is usually the sentence, but then we can also try and extract meaning and do translation and so on top of that. So we've got this progression of transductions, and a very useful framework for that is these weighted finite state transducers, and that's the fundamental part of a lot of speech recognition systems, including the one used at Google. They're a very good way of representing these finite state automata, and we can use them for building up these hidden Markov models for very complex things, like the hidden Markov model for basically all of spoken language. We can build that from these components. So one of which is the lexicon, which basically for every word in your lexicon, we map it into the sequence of phonemes. So that's basically the pronunciation dictionary. But a finite state transducer, we have these probabilistic weights. So basically this representation here says that I have a series, that the call, the word call, is made from three transitions, a K, an OR, and an OL sound in sequence. And then dad has a D, D sequence. So that's my lexicon transducer is just the words in parallel. And maps from words to phonemes. But then I can compose this with a grammar which actually says which word sequences can follow each other. So in this case, I have a very restricted language model which says I can only have the utterances call dad or call mom on my phone. So I can take, basically, I can have a grammar which says I have call dad and call mom, and I can compose that with the lexicon transducer, there's sort of a set of mathematical operations on these graphs to build these complex FSTs. In this case, we now have a graph that maps from phonemes into the words in sequences. And I can put language model transition probabilities to say there's a 50-50 chance to go between, after I've said call, it's 50-50 between dad and mum, or I can learn that, in practice I call dad more often than I call mum. So that's basically how we build the hidden Markov model graph. Now we want to model the acoustic probabilities with an acoustic model. And as I said, the dominant paradigm for that was Gaussian mixture models. There was a lot of machinery built on top of Gaussian mixture models. They're a very good way of approximating probability distributions. Basically, you're modeling the probability of an observation given a class with a mixture of Gaussians. So it's a weighted sum of several Gaussians. So I've got, say, maybe 5, maybe up to 64 Gaussians in a mixture, trying to model a distribution where I'm learning the mean and variance of each of those Gaussian components. They may be, very often they're diagonal covariants, so that if you have an n-dimensional space, this was typically, say, 39 dimensions. If you have a diagonal covariance, you've only got 39 means and 39 variances for the per component. If you have a full covariance, then you've got 39 squared. It becomes a lot of parameters. And there are people who've tried to work on sort of intermediate things like block diagonal to keep the number of parameters down while having a richer expression. But mostly people just control the expressivity by adding more components. It's linear in the number of components per acoustic unit. So each of our acoustic units, these context-dependent states typically, is going to be modeled by a mixture of Gaussians. And you train it by the EM algorithm, the expectation maximization. So the M step is you force an alignment. So you basically take your words and you work out which state corresponds to each of the acoustic vectors. That's the maximization, taking the maximum likelihood state sequence. And then given that alignment, you estimate the parameters. You work out the mean and variance of each of these components given the things that these labeled frames that you have. So basically the forced alignment labels your frames, and then you collect all the things that are labeled with a particular label, and then you train this mixture of Gaussian on those things. We had a very complex procedure for Gaussian mixture models where you slowly increase the number of mixture components. You do all kinds of things of like adding context dependency over time. So you repeatedly re-estimate these distributions, of the order of a few hundred times over your entire data set to successively build a more and more complex, a more refined speech recognition system. But if you have this alignment, you've done an alignment step, so you can align, if you have a model, you can do the alignment on every utterance in parallel. So it's very parallelizable. That's one of the advantages that Google had of being able to run this on massive clusters. Having done the alignment, you then collect you collect all the information about each state, and then you can train the mixture models in parallel for all your, say, 10,000 mixture models. So it's very parallelizable. But the disadvantage that Gaussian mixture models have compared to neural networks is that basically each frame is only used to train that specific model. So if I say this frame is a K1.57, then that frame is only used to train that particular model. So as I increase more and more states, then I need more and more data to train those states. And there's no generalization across the data that isn't aligned to a particular state. So it's very parallelizable, but doesn't make efficient use of the data. This is about the forced alignment procedure. How do we come up with the labeling for each acoustic vector? We want to know which phonetic state it belongs to. So on the bottom here is a soft alignment that was produced by one of our systems. So you have the posterior probability of each of the acoustic units. In this case, it says, how could something? I'm not very good at reading the phonetic transcription. But basically, the initial state, for the first few vectors, the silence state is very high. We have some silence. then the silence probability goes down to 0, and the h sound goes up to probability near 1, although there's some confusion there. So we've got a soft segmentation here, where we can have a hard or a soft segmentation, where we make a 0-1 binary classification of each of these things, or we can do a probabilistic classification. We can do this, given an acoustic model, whatever that model is, to get a set of labels for training our next iteration of the model. So we do this if we have a transducer. In this case, this is the phone level transducer. We can compute the state likelihoods at each time t incrementally by basically we compute the state occupancies for each frame. We compute them for the first frame, and then given that, we can compute them for the second frame, and compute that given the third frame. And we can find the likelihood of each of these states over time. And if we want to find the best path, which would be for a Viterbi alignment to get a single training example, we can actually do the max probability. And I'll show that in these slides. So again, we've got this the cat transducer. I've got the phones going up on the y-axis and time going across the x-axis. And if we run our probabilistic model, could be a Gaussian mixture model or a neural network, we get a probability for each of those phonetic classes, for each of those observation vectors. So those are what I filled in on the left. I've just filled in some of them. And now we want to work out the probability of getting to a particular state at a given time. We start our algorithm off with, we're in the start of sentence state. We know that all the probability mass is there. And then we can just combine the acoustic probabilities with the transition probabilities. So from the start of sentence state, the only place we can go is to the v state. So we know that must involve emitting the sound. So we take the 0.6 probability of emitting the in the first frame and use that as the state likelihood. Now from the state, we can either stay in the state, taking the next the probability, or we can transition to the E state. So at time 2, we have a branched probability. The probability mass has divided. We can work out these state occupancy likelihoods for state 2. We can keep on doing this, and we can either work out the total probability of being in a state by summing the probabilities when we get 2 arrows converging on a state, or we can take the max at each stage when we want to find the best path. So if we keep on doing this and take the maximum probability, we can get the best probability path, and that is our alignment. So that basically gives us one label for every acoustic frame, and that's what we can use to train our model. Yes?
You just say, like on the left is a transition matrix for different Markov chain. Like, how do you get from 0.6 to 0.15?
So I have a 50% chance of taking either of the branches. And that's not recorded here. So I've got the probability of going into each of those states. I multiply the probability mass that I have by 0.5, and then I multiply in the observation probability of the next vector as well. So I had 0.6. There's a 0.5 probability that I stay in the TH state, and a 0.5 probability that I observed a TH as well. So that's why the 0.6 went down to 0.15. That's the idea there. And then, I can normalize these because clearly, my likelihood at time t was 0.6, but all the probability mass was there. This was just a likelihood. I can convert it into a probability distribution by normalizing. And as I say, you can either be keeping track of the best probability or summing. In this case, I haven't had 2 states converging. But that's how I build a label for each state. And that was used for Gaussian mixture models, but it's also how we get our labels for our neural networks. And in decoding, we do much the same thing. Only now, instead of having a straight-through graph where we know exactly what was said, now we have the complete graph of all of spoken language. So this is just a simple representation of the grammar, where in this case, I can start with one of 4 words. And if I have the as the first word, then the next word can be cat or dog. I can attach pronunciations to all of these by composing with the lexicon. Now I get this massive graph, but there are lots of optimization techniques to make it feasible to search on this graph and do the same propagation of probabilities through the graph using the observations. So the graph embodies the language model probabilities, and then I am adding in the acoustic model probabilities. And typically, we do a beam search through this massive graph. We only keep the best paths at a given stage. We expand all those paths and then just keep the best extensions of those. And so we might lose the best path in just through that search, but by making it tractable by keeping a limited beam. So now I'm actually going to get to neural networks, finally. So as I said before, the first main use of neural networks in the neural networks were used in these 2 different ways back in the 90s. You can either use neural networks to compute features, or you can use neural networks to actually estimate the probabilities. If you compute just the features, then you can feed the features into a Gaussian mixture model and do all the probabilistic modeling with a Gaussian mixture model. And you get lots of tricks and techniques with Gaussian mixture models. So people develop things like speaker adaptation that allows you to take a Gaussian mixture model and train it on a large corpus of data. And then when you have a very few utterances from a new speaker, you can adapt that model to that individual speaker. That was made very efficient with Gaussian mixture models, and people are still struggling to be able to do that efficiently with neural networks. So for a long time, particularly IBM had very good Gaussian mixture model systems, and they continued to use these neural network features and get very similar performances in things like speaker adaptive systems. So one way of getting these low-dimensional features is you just train a neural network. So you feed in your acoustic features, you train a neural network to do classification, but you feed it through a bottleneck layer where you choose the dimensionality of that bottleneck layer, and you use that, the activations of those neurons as the features that you're going to feed into your Gaussian mixture model system. Or some people actually use the output layer posteriors or the logits from the output layer as their features. People found that they could do these, they could get good results with these features, even better if they concatenated them with existing features. They're still limited by the dimensionality of Gaussian mixture models. So typically you would take, say, 39-dimensional PLP features, feed them through this nonlinear representation to train some neural network features, concatenate the resulting features with your 39, and then do a linear dimensionality reduction to get you back down to 39, which was what you could handle with your Gaussian mixture models. So in the early 2000s, that was the main use of neural networks. It did outperform just sort of conventional hand-coded features. And for a while remained very competitive, but now pretty much everybody is using neural networks as the probabilistic model. So that is traditionally called a hybrid neural network model. So it's a hybrid neural network hidden Markov model, but basically we've just replaced the Gaussian mixture model with a neural network as the probability model. So here, we just train the network as a classifier with a softmax across our set of phonetic units. So that could be our phones, 40 of them, or it could be our context-dependent units, 10,000. We've even done experiments up to about 50,000, but that's a very small softmax compared to language modeling experiments. You just train a softmax, and it will converge to the posterior probability across the phonetic states. Now, our fundamental equation of speech recognition was written in terms of the likelihoods, likelihood of the data given the state. So what we do is we use Bayes' rule to take our posteriors from the neural network. And in equation 5, we can write that as a likelihood that we can use in our fundamental equation of speech recognition by scaling by the prior of the class. So you need to divide your posteriors that come out of the network with the class prior. And the P of probability of the observation, we don't know what that is, but it's the same for that observation across all time. So that is basically a constant as far as choosing between the different paths. And basically, all of this probabilistic mathematics is being done in the log domain, because if you did it in the probability domain, you very quickly get overflows. It's much easier to do it in the log domain, so you're adding log probabilities. And in practice, people found that basically just dividing by the prior doesn't work as well as if you use this fiddle factor, which we call prior smoothing. But just as with language modeling, if you multiply by the language model probability, people find that you don't get as good results as if you weight the acoustic model versus the language model. So you typically have a language model weight. And how big that should be is usually determined with cross-validation. So if we train a fully connected neural network, so our initial system took 26 stacked frames of 40-dimensional MEL filter banks. These are the kind of features that we might learn. I'm not sure if you can see that very well. But basically, they're very localized. Basically, we're picking out local features in these, basically the image patches. So here's a grid of many different filters. So each thing between the black lines is one filter. It's basically one neuron of the first layer, hidden layer of the neural network. And the weights that feed into that neuron from the different input features are visualized as an image. So we're getting these very localized features which look like the sort of Gabor filters and so on that you get from image convolutional networks. Well, basically, they're looking at picking out the presence of particular frequencies, particular transitions, sometimes they're angled, at a particular time relative to the frame that we're trying to classify. And typically, of 26 frames, we're trying to classify the 21st of those frames. So we give a little bit of future context, speech into the future, and a lot of past context. The further we wait, we delay the signal to have some future context, the more latency we have in our speech recognition system, the slower we get our results. But a little bit of delay helps us a lot with the classification. So in terms of neural network architectures for speech recognition, people have tried all the sort of basic architectures. The first systems were fully connected. You feed in these stacked features. You just have lots of fully connected layers going to, initially sigmoid networks. Then we switched to ReLUs. We basically ended up with networks about 80 million parameters, sort of 8 layers of 2,000 units, and then a 10,000, 20,000 output softmax. People have also applied convolutional networks. And then more recently, we got much better results with recurrent neural networks. So convolutional networks for speech have a very long history. They were first applied back in 1989. More recently, one of the sort of state-of-the-art systems uses dilated convolutions, which is also what is used in the WaveNet architecture for speech synthesis. WaveNet works on the raw waveform, but has also been applied for speech synthesis, but has also been applied in a small way to speech recognition. In the sort of more modern systems, people debated a little bit of whether you should use convolutional neural networks in the time or the frequency domain. Basically, a time delay neural network is basically a convolution in time. You basically take the same filter and you apply it repeatedly over time. Even a fully connected neural network, you're applying the same network at every time instant. So you are convolving that network over time. But when you're classifying a particular frame, people looked at doing convolution in time and then pooling. And the problem there is that pooling throws away the timing information that is actually quite important for speech. So pooling in time is a bad idea, basically. But doing convolution and pooling in the frequency domain has been very useful for some teams. It's not sort of unequivocal that like we did a lot of experiments where we didn't get gains by doing convolution and pooling in the frequency domain. But the argument is that if you do pooling in the frequency domain, you throw away some of the variation in pitch between different speakers. So a male voice versus a female voice is typically lower, but you want to recognize the same patterns whether they occur at a high frequency or a low frequency. But on the other hand, you don't want to throw too much of that information away because that's where all the speech information is in the variation in the frequency. So I would say it's still a little bit open, as undecided whether convolutions are really important or whether being basically fully connected in the frequency domain can be just as good. And all of these things are going to be dependent on the type of data that you've got, the dataset size in particular. How many parameters do you have? Recurrent neural networks, as I said, they go back to the 1990s too. Robinson and Folside were applying them to speech recognition. They were sort of simple recurrent networks called Elman recurrent networks. But Alex Graves et al. Applied LSTMs to speech recognition on some smaller tasks. And then we took LSTMs, did this extension of adding a projection layer to keep the dimensionality manageable, and applied them to very large vocabulary speech recognition tasks, and deployed them in production. They took over from the previous fully connected feed-forward neural networks. One of my colleagues, Tara Sainath, developed this variant, which she calls the CLDNN, which basically has a convolutional layer on the front end, which does frequency convolutions to get this invariance. So there's some frequency convolution and pooling, but then feeds the features from that into a deep LSTM, and then uses a DNN at the very output layer before feeding into the softmax to get some fully connected, because there's less need for the temporal processing at the output. She's shown improved results for this. Again, I think other groups would dispute whether this is really essential. Bidirectional neural networks, where you're letting the data flow back from the forward from the beginning of the utterance towards the front, and from the front of the end of the utterance towards the back. That definitely helps with speech recognition. The problem is that to be able to run a bidirectional neural network on a speech utterance, you have to have the whole utterance. So for a lot of tasks like natural language processing, you typically do have the entire sentence, and you can process it all at once. But for speech, it's produced over time. There's a latency involved in doing speech recognition. We've focused very much at Google on getting the results back to the user for a voice search as quickly as possible. So we want to be recognizing the speech before the person has finished speaking the utterance. So the audio streams from the microphone to the server and is being recognized while you're still speaking, so that we've done a lot of the computation ahead of time, so that when you do finally finish speaking, there's only a small latency before we can finish the utterance. And we even do tricks like, when we're not sure if you finished speaking, we hypothesize ends of sentences and go and do web searches based on the partial query that you've done so far, and start streaming that back to the user until we can decide whether the user really has finished speaking. And if we do decide, yes, they did finish speaking back then, we've already got the results at the phone. So you get a very low latency for some utterances. So for a live system, bidirectional neural networks are impractical, because you have to have all of the utterance. But for things like YouTube, where we're processing it offline, then we can apply bidirectional LSTMs. And when we're processing at speech frame rates, so 100 hertz, 100 frames a second, the dependencies that we care about are not really very long range. The kinds of long range dependencies that people say, it's hard to model long range dependencies with LSTMs. those are of the order of 100 frames. But typically, like for the fully connected speech, we only had a quarter of a second of speech. That was as much as we needed to do a fully connected neural network. We can easily model those long-range dependencies with those relatively short-range dependencies with an LSTM. But things like stacking multiple frames together, so we typically take 8 frames, and then downsample, so we actually skip 3 frames at a time. Those things have been found to help with speech processing with LSTMs. So typically, the LSTM now is running at every 30 milliseconds. We do a forward propagation of the LSTM. This is one recent paper. This was from Microsoft, who also have a very strong speech recognition group. They focused on the switchboard data set, which is the spontaneous telephone speech, which is the biggest major benchmark for speech recognition. And they touted this paper as reaching human parity, because they actually did a comparison experiment on humans recognizing these sentences, and they actually beat human recognition performance on 2 of these data sets. And basically, from my reading the paper, they talk a lot about their convolutional neural network, which they actually seem to say is slightly better than their LSTM. But in the end, the system that they used to get this human parity was an ensemble of 4 bidirectional LSTM neural networks. They also fed in I-vectors for speaker normalization. So an I-vector is an embedding of audio. You feed in audio, and you train a classification network to distinguish between speakers. So this gives you a representation of who the speaker is. And if you can feed that in, it helps the neural network to normalize for the speaker and gives a slight improvement in recognition accuracy, if you have enough data to train the speaker normalization on the speakers. I did some of this for voice search and found that our utterances are so short that it's very difficult to get this to work. And they had a massive n-gram and an LSTM language model interpolated to get these best state-of-the-art performances. So now I'm going to talk a little bit about how we train neural networks. Gaussian mixture models were trained with maximum likelihood criterion. The conventional neural network training, we use cross-entropy loss. We're doing classification. We typically have these binary targets where we've said we've given a one-hot label to each frame, but we could possibly have a soft alignment where we've given a probabilistic model. And we train cross-entropy to maximize cross-entropy. Another system that was proposed by Graves et al. Is connectionist temporal classification, which is basically, it's a set of changes to the standard objectives which come together as a sort of a package called CTC. The main difference between CTC and a conventional system is that there's this additional blank symbol where you basically allow the network not to commit to what the current frame is. And you just allow, it's very easy to model in the FST framework, where basically you just put a blank symbol between each of your phone symbols, and you make it optional. So we have these skip transitions that go around the blank symbol. And basically, any transcription that has a k followed by, with any number of blank symbols, followed by an a, followed by any number of blank symbols, followed by a t, is considered to be cat. And this system has been particularly useful for doing continuous realignment. So you don't need an initial model to give you an alignment. You just take an untrained neural network, you try aligning, you know that the k frame has to be somewhere before the a, has to be somewhere before the t, because you have the transcription. You know that this utterance says cat somehow. You don't know where the alignment is, but you do the best job you can, even with your untrained neural network. And this is found to be, has been found to stably converge to a reasonable alignment, whereas it's much harder with a conventional system. If you don't have these blank symbols, it's much harder to get to be able to bootstrap the system from no alignment. We typically train a conventional neural network from the alignment given by a previous neural network. And in the first stages, we trained those from the alignment given by a previous Gaussian mixture model system. And typically those original Gaussian mixture model systems were ultimately trained from something that was trained on Timit, where they were hand labeled. We've shown that you can bootstrap this neural networks, but CTC makes that a lot easier. They always use the soft targets instead of the Viterbi hard alignment. And one other detail is that you don't need to scale by the posterior for the probabilistic formulation of CTC. But what we found is that it gives very similar results to conventional training. It was essential to do the downsampling to get CTC to work, but it ended up giving very similar results when we did the downsampling for the conventional system as well. This is what a CTC alignment looks like. So now you've got these spikes of the actual phones separated by what's shown here with a dotted line, which is where the blank symbol occurs. So instead of forcing silence to be high for any frame until we transition to the next symbol, now we just give a spike saying there is some silence here. It goes back to the blank symbol until we get a definite evidence of the next phone, and then we emit a spike for the next phone. All the decoding and so on that we have with our conventional system works exactly the same. We just use the new FST with the blank symbols in, and we can just use the same decoding. We get very similar results. One thing that was found to help very much with Gaussian mixture models, there was a lot of effort done on this in the 90s and then into the 2000s, is using sequence discriminative training. If we use cross entropy, we're basically trying to maximize the probability of the true state sequence given the data. But what we actually care about in the end is the word error rate of the complete system. That's like the system making mistakes. So people spent time trying to design losses that were differentiable, so we could still use them with neural networks and Gaussian mixture models, but they're closer to what we actually care about. And they were applied with Gaussian mixture models. People came up with various modifications that made it stable for Gaussian mixture models in the 2000s. And then they were applied for neural networks. There's some precursor papers that people were doing very similar things back in the 90s as well. But people came up with these different criteria. The two most popular are BMMI and SMBR. So MMI is maximum mutual information, and SMBR is state minimum Bayes risk. But basically, I can show it better with a graph rather than going through the equations. But basically, with forced alignment, we give one alignment. We say this utterance says call mom. With sequence discriminative training, we do a full decoding. We allow the system to recognize the utterance. We know what the truth is, but we see what mistakes it can make. And we make a limited language model which only has its the mistakes. Either if it got the top one wrong, then we definitely want that in, but also anything that was similar that it thought should have high probability. And basically what we want to do, so in this case, the truth was call mom. If the network gave us a high probability for call dad, then we want to contrast that mistake with the truth. So where it got call correct, there's no change to be made. The model is doing a perfectly good job. But where it said it gave dad a high probability, then we want to tell it dad was bad in that case, and you want to upweight mom. So we tweak basically we design a loss to make this distinction, and we can backpropagate the gradients of the loss. But essentially what it's doing is it's pushing down whatever gave us a high probability for dad and pushing up what gave us a high probability for mom. Not just telling it the true target is mom, that's what you have to get. We can actually, basically, we're looking at the mistakes it makes in the context of the language model. So decoding was done with a language model. We know that certain things were impossible to say. In our language model, we may say, call Fred is impossible. But our acoustic probabilities could have given Fred a high likelihood. And in conventional training, we'd be pushing those down. We'd be saying, no, Fred, the f phoneme at this location was wrong. We'd be spending effort pushing it down with the gradients. when we have the language model, we know that there's never going to be an F sound at that location in our language model. So we don't need to be pushing down on the F. We only need to be pushing down on the D sounds, which are allowed in our language model. So this is a way of training the acoustic model to compensate for the language model that it's going to be used with. And that's by basically looking at so we've got a sum on the bottom of all the possibilities of the different paths through the network, but we're looking at the probability of the truth on the top. And we're contrasting those two things. So for MMI, we're pushing up on the good thing and pushing down on the bad things. And this has basically been found with Gaussian mixture models to give about a 15% word error rate improvement. So it would reduce our word errors by 15%. And we found exactly the same with neural networks. And whether we trained the neural networks with cross-entropy or CTC, the same system, exactly the same, could be applied, and the sequence-level discrimination, discriminative training, gave this 15% relative improvement. Now I'm going to talk a little bit about sequence-to-sequence, and some of the new neural network architectures, and then I'll finish, and we can do a couple more slides from speech recognition on Thursday. So far, I've been talking about what I call conventional speech recognition systems. And in my opinion, the conventional speech recognition systems are still the best systems. They give the lowest word error rates. But there's been a lot of work on alternative models, which are getting very close in performance. And one of these is looking at sequence-to-sequence models. So you've seen these used for things like machine translation and so on. People looked at applying these to speech recognition. So this is, you feed in all your observations into an LSTM, you build up an LSTM state, and then you decode that state using a language model type system to emit the symbols. The trouble is, it's not really very good for speech. The utterances are very long. If we look at we have hundreds of frames of speech. And speech is monotonic. Basically, the acoustic signal is monotonic with the text transcription. Machine translation, you have problems of reordering and so on, things like, so you need to be able to output in a different order to what you see. But speech is completely monotonic. So you don't know the exact alignment, but you do know that once you've emitted a symbol for something, you don't need to think about the audio of that anymore. You've used that audio up effectively. So it doesn't really make sense to memorize a speech utterance and then try to emit that as a set of symbols. On the other hand, attention makes more sense. So if you embed the entire utterance and then use attention to attend over that embedding as you emit symbols, then that makes more sense. You haven't memorized the entire thing. You're just attending over a representation. And that has been used in a couple of papers. So there's this work by Chorowski and the work by Listen, Attend, and Spell, which was done at Google, which basically uses a sequence-to-sequence model with attention. One thing that's a problem here is that your decoder is emitting symbols in your language, and very often people have used this for working in the text domain, so they're emitting characters rather than phonemes. And it's very difficult to incorporate a separately trained language model. When we train a conventional system, we train an acoustic model on, say, 4 million utterances of speech, but we'll train the language model on maybe 100 billion tokens of text. We've got vastly more text data than we have acoustic data. So when you train a sequence-to-sequence model, it's modeling the language model, but only based on the data that it was shown in training, which is the data that you have acoustic information for. So it's very difficult to incorporate a language model in the same way as you can in a conventional system. You can output you can do a beam search and then rescore using a language model, but it's not as integrated into the search and therefore not as useful as we can exploit a language model in a conventional system. But this is doing a language, so if you had enough data, potentially it would learn the language model of the language that you're modeling, and you could, if you had enough data, this might be a single system that could go from the acoustics directly to the characters or words in your language. This is some work that was done here at Oxford in collaboration with DeepMind, with Professor Zisserman here, which is extending the listen, attend, and spell model to do lip reading. So in addition to feeding acoustic features, you have another LSTM which embeds visual features. So you crop out bounding boxes around the lips, feed those into an LSTM, and the decoder LSTM attends over both the acoustic data and the visual data. And this model, you can jointly train it on acoustic and visual data, or where you have only acoustic data, you can train just the acoustic part, and you can also do dropout, and you can train only on the visual part. So now you have a combined model that does acoustic recognition and visual recognition, or combined audio-visual recognition. So this was recent work. It was trained using scheduled sampling to model the output distribution sequences, and was the first system that I know of that beats beats a conventional system on clean audio. So if you have an acoustic system, you get a certain word error rate. So the audio only is here, the word error rate is 26.9. If you add in the video, even in clean speech, then you get a reduction in the word error rate. Typically before this, lip reading systems were used only in heavily noised conditions to disambiguate sounds that you couldn't hear anymore. But this shows that you can add visual information and get improved speech recognition, even in clean speech. But it's even more dramatic if you have noisy speech. And you can get pretty good error rates just doing lip reading. So the bottom graph shows only the watch, attend, and spell. So using the visual side of this to do just lip reading. One problem with these attention-based models is they require embedding the entire utterance before you can do the decoding. So Navdeep Jaitley, who was the intern who originally developed the Google deep learning system for speech recognition and did this as a full-time employee, he developed the neural transducer system, which is basically similar to an attention system, but it moves left to right through the utterance, considering chunks of the audio and emitting a set of sequences, a set of symbols for that chunk before moving to the next chunk. And so it moves left to right. Doesn't require the entire audio to be embedded. So it allows you to have this sort of online processing so you don't get the latency. So it could be a potential for live streaming recognition. So I think I'll end there and save the other slides for Thursday and add them onto the text-to-speech slides. So if you have any questions, I can take questions, or you can come and talk to me afterwards.